Hey everybody, welcome to the first lecture. My name is Zach Stelter and I'll be your instructor for the course. And we're going to start talking a little bit about science. And this is a great place to start because I get the sense that there's a lot of people that are not entirely sure what science is and what it's not. Science is sort of this catch-all word that you could put on a coffee mug or even like a shirt. So you might see some shirts out there. They might say something like "science is real." What does that mean? Or science, true whether you believe it or not. Or the more I study science, the more I believe in God. A quote from Einstein. Okay, sometimes science gets thrown into a whole list of notions here. So you can see there's a bunch of paradigms that are being encouraged and supported on this shirt, but then amongst them all, you know science is real. Okay, science is magic that's real, or the be-all end-all because science. So what is science? There's an interesting quote here. This is from Anthony Fauci, who was sort of a leading voice of the scientific community in all of the uncertainty surrounding the pandemic. And we have a quote here saying he's upset with people that aren't listening to the mandates and they're not following the rules. And he says at the end here that they just don't believe science and they don't believe authority. And this, I think, gets to the heart of a lot of the frustration from that pandemic. And the question, though, I would ask is science a belief system that we're just supposed to believe? I don't think so. Okay, and this is actually has a long storied history here, and I'll try and unfold just a small snapshot of it. There's a difference in what's known as natural philosophy and modern science. And so for hundreds of years, in the days of old, generally how it worked is you would have really bright people, and they would say things, and people would just believe them. They wouldn't think to question them. They wouldn't think to put them to the test. They wouldn't think to critically, dissect the logic and any of that type of stuff. They just believed them. Okay, so for example, Aristotle, a very famous philosopher, way back in the 300s BC, one of his conclusions was that heavier objects fall faster than lighter objects, and that would be an intuitive conclusion. That's something that I wouldn't really dispute either. And many people didn't for hundreds of years until Galileo Galilei, who many would revere as the father of modern science, decided to put that conviction to the test. And I don't know if this is true or not, but legend has it he climbed up the Tower of Pisa, which is where he was from, and he dropped two objects of the same size and the same texture, but one was heavier and the other one was lighter, and they fell at the same speed. And we now know that they are both subject to the same force, the same acceleration of gravity, which is 9.8 meters per second squared, and so they accelerate at that same rate. Okay. Also, Aristotle said that the moon is perfect without any blemishes. The philosophers of old thought that the glowing spheres in the heavens were these sort of beautiful orbs that had no, the heavens were sort of the reflection of divine perfection. And Galileo Galilei actually invents a rudimentary telescope and looks at the moon, and these are his sketches, and you can see he was seeing all the craters and the pits and things. It looked like this moon had actually been smashed up a little bit. It wasn't quite the same glowing, sphere of perfection that the philosophers would claim. Okay, and then just one more. Aristotle thought that all colors come from white and black. So you mix a certain amount of white together with a certain amount of black together, and you'll get blue, and then you change the proportionality, and then it would be green or something. And Sir Isaac Newton actually disproved this one. He took a prism, and he was able to see that actually white light is a collection of all the colors combined together. And so it's sort of the other way around. If you have all of the colors present in equal proportions, it forms white light. White light doesn't form the different colors. So in all of these, illustrations here, what I'm trying to show you is that people took it upon themselves to actually question and sort of dig their heels against the common notions of the day, and they put them to the test and actually collected data and ran it. They took the trouble to actually run an experiment to see if the data aligned with the conviction. And that is sort of the essence of what we call modern science. There's a great well-known quote here from Henry David Thoreau that I really think sums up the heart of a scientist. Rather than love, than money, than fame, give me truth. And if you resonate with that sentiment, you are a perfect candidate for the pursuits of science. That scientists, they value truth pretty much more than anything. And, even if the grant funding is trying to sway their results for some sort of thing that will lead to some policy change, a true scientist would say, no way, I follow the data. It doesn't matter about the money. It doesn't matter about the fame. My name could be drug on the ground for 100 miles, and I will stake my claim on what I believe to be true, and it's usually driven by data, is sort of the heart of science. Okay, my definition for science is that it is an unbiased pursuit of discovery, and you can go ahead and put that on a coffee mug for me. Okay, this is my definition. I'm not saying that's the be-all, end-all definition. You can go question it for yourself. Conduct your own experiments. Okay, but I believe that what science is, it's basically we're trying to discover things, and we're trying to discover it in a way that's not skewed by our own presuppositions, our own philosophical predispositions. We're not skewed by funding and fame. We're just trying to discover without the interpretations being skewed. And we generally make, I think, the mistake of saying science is just things like biology and chemistry and physics. Those things all investigate the natural world, and science is heavily employed in those pursuits, but you could argue that science is manifest in any field, in any arena in which we're just trying to discover without our discoveries being skewed. What is actually the truth? That is science. Like you could have computer science, or you could have other things like that that have nothing to do with biology or chemistry or physics and things like that. Now, if the pursuit of discovery is to be unbiased, it must always be subject to scrutiny. And so this is where I'm going to part ways from Anthony Fauci here. I don't believe that you should always just believe authority, and I don't believe you should believe quote-unquote science. It should always be subject to scrutiny. People should be able to come in and show data and conduct experiments and speak against the common notion of the day, the popular notion of the day, if the data holds true. It should always be subject to scrutiny. If our convictions are true, then we don't have to be afraid of what the data will yield. And that can be a little bit of a tricky process because what the data yields is often subject to our own interpretations, and that's where philosophy sort of enters into the mix. Okay, science is not a belief system we should be pressured to believe without objection, and it's not a set of ideas championed by people who have prestigious degrees or positions. In fact, I would probably disagree with a lot of popular notions that are championed by people with very prestigious degrees. I think a proper way to think of science is that it is a process. It is the process by which we discover, and that process is it has become a fine-tuned machine because of this thing called the scientific method, which we're going to talk about in just a minute. But when people say things like science is real, and they use it sort of as a way to bolster their own convictions about something, there's a great error there. And just to understand the error, it would be like me, building a bridge. Okay, bridge building is a process, and the process is only as good as the tradesman who conducts the process well, right? So my bridge, even though bridge building is a process, how good my bridge is and how safe it is depends on how good of a bridge builder I am. In a similar way, science is a process, and how trustworthy the convictions are that are yielded from the pursuit, the process, depend on the skill of the scientists involved. Okay, so to say science is real, to say something like science is real, you just got to believe science. That is not. When people say things like that, they do not understand really what science is. That would be the same thing like me trying to convince you to get on my bridge by telling you that bridge building is real. Okay, you'll get on my bridge if it looks like it's well built, right? And you will stay far away from my bridge if it looks like it is not built well. And it would be very silly for me to try and convince you to get on my poorly built bridge by claiming, well, don't you believe bridge building is real? Yeah, I believe bridge building's real, and I'm never getting on that rickety old piece of junk. Okay, so to claim that the process is real as a means of trying to convince somebody to believe the interpretations, that is just a great error. So I want to clarify that, because I think people really show their inadequate understanding of science when they say things like that. Okay, so from here, we're going to jump in to the biggest tool that we have in the unbiased pursuit of discovery, and that is this thing that we call the scientific method. The scientific method, championed by a guy named Francis Bacon in the days of old here, and there's actually a very defined process by which we conduct science, and that process has been what has helped us get leaps and bounds in discovering the natural world. And the natural world is huge. There's lots of nooks and crannies of it. There's astrophysics, there's paleontology, there's biology, chemistry. There's all these different nooks and crannies you can go, and there's plenty to discover in every of those arenas. And the way that we discover how these nuanced things work is by subjecting them to experiments and collecting data. And the experiments, designing the experiments is huge. And scientists can take convictions and data that another person found, and they can run with it and push the ball even further. And that's what's been able to allow us to get so far. We've discovered so much in the last 200 years. I mean, if you just popped open a textbook from like 1850, it would look vastly different than it does even just 150 years or 170 years later. And that, I believe, is much in credit to the scientific method. It's a very formalized process. All scientists agree to pursue their inquiries in line with the scientific method. And it just makes it very helpful to synchronize data and to expand it in future studies. Okay, here's a simple illustration of the scientific method. I'll walk you through an example here that will help present it. Okay, let's imagine that I have noticed that the test scores in my class have recently improved. Well, a natural consequence of that would be to wonder why. Okay, so then we would ask a question: why have the test scores recently improved? And here's where I would sit and scratch my head a little bit. I would think about all the things that I could possibly think, reason out the best explanation, and then I would form my official hypothesis. A hypothesis is what really drives the scientific method. This is what all experiments are going to be designed to test. And so a few features of a hypothesis: one, it's an educated guess as to why something is the way that it is. And I'll say that one more time. It's an educated guess or explanation as to why something is the way that it is. It doesn't have to be true or false. It doesn't have to be correct or incorrect to make one. That's what the scientific experiment is going to do. It's going to either support or not support the hypothesis. So the hypothesis, an educated guess about why something is the way that it is. Another feature about a hypothesis is that it has to be testable. There has to be a way that you can test the hypothesis. If you come up with an explanation for how something is, but you can't actually test it in any way, it would not be considered a hypothesis. And it would be wrong to say that hypotheses are either unequivocally right or wrong. Generally, what we do in science is we say that the hypothesis is either supported or not supported by the data. It could be that the hypothesis is actually right, and our experiment, for whatever reason, just didn't have good data and it didn't show it being correct. So you would be careful as a scientist never to say that a hypothesis is right or wrong, but rather that it was either supported or not supported by any particular data set. Okay, so an example of a hypothesis in this scenario, let's say that I notice this new energy drink floating around campus. Okay, it's 5-hour energy, and I'm not a rep for 5-hour energy, and I've never consumed it either. So the first thing that came to my head, 5-hour energy. Okay, so let's say my hypothesis is that test scores are affected by the consumption of 5-hour energy. It's the first semester I'm seeing this new energy drink. All the students have it. And it's also the first semester that the test scores improved. That might be a likely candidate. I can't think of any other reason. There's nothing that's changed otherwise to my curriculum that would make 5-hour energy the most leading culprit here in what's driving the test scores up. So then my hypothesis would look something like this. Test scores are being affected by the consumption of 5-hour energy drink. Okay, a hypothesis will generally start to carve out what is known as the dependent variable and the independent variable. Okay, and I'll just pause the video here for a second, see if you can determine which one is which. I will say that here's the two variables, test scores and consumption of 5-hour energy, but which is the dependent variable and which is the independent variable? See if you can figure it out. Okay, the way that you know you've found these variables, or you've correctly identified them, is that they only make sense one way. So the answer is that the test scores are the dependent variable, and the consumption of 5-hour energy drink is the independent variable. And I know that because I'm saying that I think the test scores depend on how much 5-hour energy drink my students are consuming. It doesn't work the other way around. If I said that the consumption of 5-hour energy drink was the dependent variable, and in other words, how much 5-hour energy drink one drinks is dependent on their test score, that would mean that somebody that got like a 96% on their exam just involuntarily chugs 5-hour energy drink, and somebody that got an 82 on their exam only drinks 2 cans. They don't have any choice in the matter, that how much they drink is totally dependent on their test score, and that doesn't make sense. So it usually only works one way around. The dependent variable depends on the independent variable. The dependent variable is usually the one that you always measure, and that's a little bit misleading because we would be measuring how much 5-hour energy drink the students are consuming. But and so sometimes we can measure the independent variable as well, but most textbooks will say the dependent variable is the one you're measuring. In other words, this is the one that we're tracking. We're interested to know what the scores are, and we're going to make sure that we record those scores because we think those scores are dependent on the consumption of 5-hour energy drink. The independent variable is one that we manipulate or change. And so a good scientific experiment will have different variations or trials of the independent variable, and in theory it's only the independent variable that's changing between the trials and the conditions. Nothing else is changing, and that would be a perfect scientific experiment if you could accomplish that. It's nearly impossible, if not impossible, to accomplish that, but it's sort of the gold standard. Any scientists, when they design an experiment, that's their main goals. They're trying to create a scientific experiment where there are different arrangements, different trials or conditions of the independent variable of interest, and nothing else is changing besides just the independent variable. Okay. One of your big tasks in this class is to be able to identify these variables. So if I gave you a hypothesis, or I gave you like a description of a scientific study, could you tell me what the dependent variable is and what the independent variable is? That's your first big hurdle in this class, and that's one that many students often struggle with. So I have a couple of practice exercises, and I can make some more practice exercises available to you if you just want to try working through that more. Okay, once you form the hypothesis, then you might go further and actually predict the way that the variables interact with one another, and specifically what should be the outcome based upon the hypothesis of whatever study it is that you want to design. So here I'm saying I still have the two variables, dependent variable, independent variable, but I'm saying that the test scores will increase if there is an increase in the consumption of 5-hour energy drink. Here we have a couple of things that can happen. These are directly proportional relationships. In other words, if you increase one, the other one will increase, or if you decrease one, the other one will decrease. Okay, so if I decrease the energy drink, it might decrease the test scores. If I increase it, it might increase it. That's directly proportional because you're increasing one, it increases the other. It's the same effect. You can also sometimes have inversely proportional relationships where if you increase one, it will decrease the other. Okay, but generally be one or the other. All right. Then you would do an experiment to test the prediction, and here, to design your experiment, you have to figure out what your independent variable is, and this can sometimes be tricky. If the subject matter is very complicated, it can be difficult to figure out specifically what the dependent variable is or what the independent variable is, and I would say even professional scientists still have trouble with this when they do their studies. Once you get into designing a study and you're bound by funding and you're bound by the equipment at hand and the personnel that you have, your study can sort of get limited, and sometimes we can lose track of the dependent variable and independent variable. Okay, and on some studies they might have multiple different parameters that they're looking at, so there's kind of like several nested studies in one big study. Okay, the independent variable is the one you change. If you were to graph it out, that would be the one that's on the x-axis. The dependent variable is the one that's on the y-axis, and just to illustrate this here, if you were to draw a chart and have axes here, the x-axis is the horizontal one and the y-axis is the vertical one. Okay, you would also want to keep in mind controlled variables. Controlled variables are the things that you keep constant in between the different trials or conditions or manipulations of the independent variable. So for example, let's start to think about how I would design my experiment to test this hypothesis. You would probably think that I would do something like take my class, assign them into cohorts, and assign them how much energy drink they're going to drink. Don't worry, I'm never going to do that to you. But I would assign, let's say this group of students is drinking 2 cups a day. This group of students is drinking 4 cups a day. This group of students is drinking 6 cups a day of 5-hour energy drink. And we're going to see, if those people that are ramped up on the energy drinks, studying all night long, that's going to increase their test score. Okay. So if those were my two groups, let's say, or my different groups, let's say I have 0 cups a day, 2 cups a day, and let's say 4 cups a day, and I assign you into one of those groups. Now these are my different conditions of the independent variable. I've got groups of students assigned to each one of these groups. The only thing in theory that should change is the consumption of 5-hour energy drink. These students should have a lot of controlled variables kept in mind. So the controlled variables would be things like they should get the same exam. Okay, if I give one group of students a hard exam and another group of students an easy exam, I don't know if the difference between the test scores is due to the difference in the exam or the independent variable of interest, which in this case would be the consumption of 5-hour energy drink. So these students should be getting the same exam. They should be roughly the same demographic, the same number of males and females in each group, the same blend and mix of socioeconomic status. The demographics would be a huge thing to try and control in this study, and it would almost be impossible. Well, it would be impossible to control perfectly, which is why the perfect experiment doesn't really exist. But I, as a researcher, the more closer we are to that gold standard, the more likely our data will be reliable from the study, and we can trust the conclusions that are wrought from it. Okay, so the same exam, you want to consider the demographics, you want to consider the testing times. If I put one group of students in a nice quiet library and another group of students in like a techno dance party that's full of chaos, it could be that the scores are due to the different environment, right? So controlled variables are all the things you want to keep constant between the groups. and it's probably one of the greatest challenges of any scientific experiment is controlling it. Any variable that gets introduced that's not controlled, we would call an extraneous variable, and any extraneous variable that's introduced into the study design will be a source of ambiguity in our data. We won't know for sure if the data is reliable, because we won't know if it's due to if the findings of the dependent variable are due to the changes of the independent variable, or if it's due to the extraneous variable, like technomusic. Okay. Also, generally, a good experiment will have what we call controls, and this is a little confusing. Controls are not the same thing as a controlled variable. Controls are actually groups or variations of the independent variable, groups that you include that are used as sort of a quality control metric. So like a really great illustration of what a control would be, I use this one all the time, would be like if I was studying antibiotics and I had test tubes, and let's say I put ampicillin in one, and let's say I put like erythromycin in the other, and then in the other one I just put water. Okay, and I put bacteria in all three tubes, and I came back, 2 days later, and I saw that there was no growth in the ampicillin tube. I might go, oh wow, the ampicillin worked, right? Or if I saw there was also no growth in the erythromycin, I would go, ooh, the ampicillin and the erythromycin worked. These are great drugs. And if I just stopped there, I might be inclined to think that these drugs were really effective at killing the bacteria in the tube. But there would be a major problem if I pulled out my tube that had water in it and noticed that also the bacteria were all dead in the water tube, right? Because water is not an antibiotic, and it should not kill, in and of itself, should not kill the bacteria so long as they're in some sort of growth medium. So if I found out that this tube, this would be what's called a negative control. We would not expect there to be any observable effect of inhibiting bacterial growth due to the antibiotic in this tube of water. So a negative control would be one where you're not supposed to get the intended result. A positive control would be one where you absolutely should get the intended result. And if there's any irregularity in the controls, they tell you there's something awry with the experiment. So for example, in this case, if I saw that there was no bacteria growing in the water tube, then there must be something else that is killing all of the bacteria, not necessarily my antibiotics. So controls, they're like a quality control. You look at the positive control, see if you got what you were supposed to get. Look at the negative control, make sure you didn't get what you were supposed to get. And then if both the positive and the negative control check out, then you could be more assured that the data you're getting in your other trials or conditions is reliable. There's not some other extraneous variable in there causing ambiguity and making the study unreliable. Okay, these are all ripe for lots of exam questions. So on the exam, for this chapter, you can bet your bottom dollar that I'm write out a scenario of a scientific experiment, and I'm going to ask you what the independent variable is, and I'll ask you what the dependent variable is, and can you spot what a controlled variable might be, and can you even spot what something like a positive or negative control would be. And I have practice problems that I can give you. Just reach out if you want those. I'll put them on D2L. This is a sort of a very big hurdle to jump through right from the gate in the class, and you'll need all the practice that you can get. Okay, but there will be a good amount of questions on the exam about all of this type of stuff. It's very important as you start treading the waters of science. Okay. All right, after you do the experiment, you would analyze the results, and here's where you can have one of two options. Either the hypothesis is supported by your results, or the hypothesis is not supported by your results. You wouldn't want to say that the hypothesis is true based upon your study and the hypothesis is false based upon your study. Your study may not be the be-all, end-all, right? And maybe your study wasn't even done right. So you wouldn't want to go as bold to say something like that. But you could determine if the hypothesis, at least from the data that you're seeing, was supported or not supported. If, regardless of the outcome, you would want to report your results, either one of those is important. Generally we're really excited to see if our hypothesis is correct. If the data is supporting it I should say. It's always sort of sad to find that your hypothesis doesn't seem to be supported. In other words, there's probably another hypothesis that's more of a likely reason. But both of these are valuable, and this is why the scientific method is so powerful. Because what you do is you report the results, and if you were unsuccessful, if your hypothesis is not supported, you jump right into that water and you churn that thing out one more time. And you just keep at it, and you can go weed through all sorts of alternative hypotheses until you find the one that the data supports. And it allows you to weed through a million incorrect notions. And it really is a million incorrect notions you have to weed out to figure out sometimes how something works. I spent 2 years doing research at the U, and I can tell you there's a lot of incorrect notions out there. And there's a lot of times you do the study and you don't get what you thought you would get. And even some of the best discoveries on the planet came from getting results that you did not expect you would get. So, a very powerful tool because it can just keep churning and churning and churning, and as soon as you are retiring from your research project, another person can jump right in and pick it back up. We have the format here. We know how to design the experiments so that they eliminate bias. And they really hone in on specifically what is the dependent variable and the independent variable, and see if the independent variable is really the cause of the effect. Okay, I've got a couple of review exercises here. You can go ahead and pause the video, but just a couple scenarios here, and I'll let you read them, and then I'll tell you what the answers are. So go ahead and pause it. See if you can figure out what the independent and the dependent variable are, what the control variables are, and if there is one, what a control group would be. Okay, so here's the answers. We have in the 16, and these are actually semi-real scenarios. I've embellished them a little bit, but in the 1600s, people believed in the theory of spontaneous generation, that basically organisms just spontaneously appear. So people thought that like flies and maggots found a rotten food because they just popped out of thin air and arrived. Okay, there was a scientist named Francesco Redi who did not believe this, and so he set up 3 treatments. He had jar number 1, jar number 2, jar number 3, and in jar number 1 and jar number 2 and 3, they all had meat in the bottom of the jar. One had no cover, one was totally sealed, so no air and flies could get in, and one was like partially covered. It was covered by a permeable substance that could let air in. And then the results is that jar 1, the unsealed jar, had many more maggots. Okay, so in this, the dependent variable would be you're trying to measure for maggot growth, basically. Are there maggots or not? The independent variable is going to be the exposure to air, basically. One's sealed, one's totally exposed, and one is partially exposed. And that's the thing that's changing between all the 3 groups. The control variables would be things like you got to have the same type of jar, you got to have the same type of meat, you got to have the same duration, how long the jar is sitting. All things that would need to be kept constant if we're really to hone in here on the effect of the IV on the DV. Okay. Over here, Alexander Fleming, studying the growth of bacteria. He returned from holiday and noticed a spot of mold growing on a petri dish and found there was no bacterial growth around the mold. This is actually what discovered penicillin, a really potent antibiotic that fungus make. So in either case, this is my embellished experiment that maybe he did or did not do. Okay, he's got 3 petri dishes. One's got bacteria only, one's got bacteria plus the mold spot, and one just has mold only, no bacteria. And the results is that there is growth of bacteria on the entire plate. Bacteria 2, no bacteria growing on the mold, and bacteria 3, no growth of bacteria anywhere, just the mold. So in this case, what's the DV, what's the IV? The dependent variable will be what we're measuring. In this case, it's bacterial growth. And the IV would be basically exposure to mold, essentially. How much mold is on the plate? None, some, a lot. Okay. In terms of control variables here, you got to have the same type of bacteria. You would have to have the same type of petri dish. These should be incubating in the same temperature, the same environment, the same location. Everything between these three plates should be the same in theory, except for how much mold is added to the plate. So actually this should probably say there is bacteria on here as well, unless it's a negative control. Okay, so yeah, that's a good thing here. Positive and negative controls are a little less clear cut in these scenarios, and they sometimes can be. It's not always the case. The scientific study has a well-defined control. But here you could say maybe the meat in the bottom that has no cover would be a positive control, and here the sealed jar would be the negative control. We would not expect there to be maggots growing from rot in a sealed container, but we would expect there to be in one with no cover. And here, kind of the same, negative control, there's no mold here, and positive control. You can make a case that those are the control groups. All right, the arch nemesis of science, you know, if we're going to go with my definition that science is the unbiased pursuit of discovery, then bias would be the total arch nemesis of science. And what bias is it's our tendency to believe something is true even if it's not. Okay, it's basically our predisposed desire of what we want to find, and we all have it. It's impossible to eliminate it completely. If you're a scientist and you've just spent hundreds of thousands of dollars trying to find some sort of thing, you would be very tempted to find that sort of thing, right? There's a lot of temptation for bias out there, and the best scientists will be those who are able to eliminate bias as much as possible and just look at the facts, try to avoid their own desires, what they want the data to be, what does the data say, what are the unbiased interpretations of it. Okay, so to help us reduce bias, that is a normal tendency in any scientific experiment, there would be things like placebos. So a placebo is often talked about in clinical trials with drugs. So people that take pills sometimes are inclined to believe that the pill is helping them, whether it really is or not. It's called the placebo effect. And so, you know, like if it was like a clinical trial for an antidepressant, let's say, it might be the case that somebody just the very act of taking something and feeling like there's some medication that's going to help you might actually make you feel better, whether the medication even works or not, right? So in that type of an experiment, it would be really important to include a placebo. This would be like a pill that doesn't have the drug in it. So everybody's taking a pill, it all looks the same, everybody thinks they're getting the drug, or they're not sure if they're getting the drug, and then it sort of controls for that placebo effect that might creep in there. And based upon placebos, that you can have either single or double blind experiments. A single blind experiment would be one where only the people that are taking the drug are unaware which they have. Do they have the placebo, the pill that doesn't have any drug in it, or do they have the pill that does have the drug in it? Okay, that would be single blind. Only the participant is unaware if they have been assigned the placebo or not. In a double-blind experiment, both the participant and also the person administrating the trial are going to be unaware. And so, you know, the samples, the drugs and things would be prepared, and then they'd be randomized, and the people that actually know who's getting the drug and who's not, who's getting the drug and who's getting the placebo, those people are not involved in the actual conducting of the experiment. They only reveal the answer once the experiment's been conducted and the data has been collected. Okay, so single, only the participant is unaware. Double, both the participant and the experiment administrators or the people facilitating it are also unaware. And a placebo is a useless entity that's included. It doesn't actually contain any active drug or is not supposed to cause any effect, but it's included just to help reduce the placebo effect. And the placebo effect, again, being one's inclination to believe something has happened to them, not because of the actual medication or the drug or the agent, but just simply because they feel that they've taken something. Okay. The other thing that's going to help with bias is that science is usually not an individual pursuit. It's usually done as a community. And so generally what happens is that you will report your work, and to report it, it goes through a whole peer review process where people will go in, they'll look at how the study was designed, they'll look at your data, they'll make sure that your study was designed well, and they'll even look at your data and see if the conclusions that you're getting from the data are reasonable. Okay, and so when we add more eyes of scrutiny onto the equation, it greatly reduces the wrong interpretation that could come from one's own individual bias. So generally the process of reporting scientific work, this process right here, it can vary. Sometimes in a college class, you might just write up a lab report and submit it to your instructor. But generally in the professional sphere of science, this is going to go through an academic journal. So it would look something like this. This is called the peer review process. That you would organize all of your findings, you would detail your methods, and there's a pretty standard format for how this is done, how you would actually write this paper. You would write the introduction, talking about why the study is important and what you're assessing. You would talk about the methods, how the study was done. You would talk about what the results are that you received and what your conclusions were from them. Those are sort of the big pieces that you're going to include in your paper. And you would submit that to a journal. And journals are just collections of people that have a panel of experts on them that are going to review these papers, and only the ones that have been reviewed and scrutinized and accepted for publication will be published in the journal. So some examples of journals like Nature and Science are some of the biggest ones in science. And generally the rule of thumb here is the simpler the name, the older the journal. Because now we have very complicated journals like this one, the Internal Journal of Neuropsychopharmacology, right? So they can get very nuanced and complicated now as science has expanded. But some of these older ones are going to have smaller names, and generally the older ones are revered as being the more prestigious ones. So it's a really big deal if you get your study published in Nature or Science. Okay, so if I was doing research, I would submit it to one of these journals, and they would review it, and they would give me feedback. Often there's several rounds, 1 or 2 or 3 rounds, and then I would revise it based upon their critique, and I would submit it again, and this goes over and over and over again until eventually the panel of professionals, they either just reject the paper and I give up, and I just say, okay, I'm done, or they accept the paper and then it's published. And so when we have this peer review process, if you're looking for articles and they're published by a peer-reviewed professional scholarly journal, you can be assured that there's going to be less bias in those articles because they've been scrutinized by many eyes, not just the individual researchers. Okay, I think we're going to stop there, and when we pick it back up, we're going to talk a little bit about the nitty-gritty here of data analysis. We're sort of going to just do an overview of statistics. We won't do a whole lot of statistics in this class, so don't worry, you're not going to have to start crunching a bunch of complicated statistical analyses for me. But there's just some really important concepts to understand in statistics, and I think if you know them, it'll really help you out as you go out into the world. There's often a lot of data presented in any article you read, even if it's peer-reviewed or not. They're going to have marketing charts and bar graphs and line graphs and things. They're very common in our world today, and some of them can be very misleading. So we'll use sort of our knowledge of statistics here to help us understand a little bit more about what's true and what's not based upon some of those graphs that you might see. So very helpful discussion. I'll try and keep it to a minimum, and that's where we're going to pick it up in part 2.